Welcome to MACSMIN. Our next talk will be by Professor Kotov from the University of Michigan, United States, about graph theoretical engineering of nanostructures. Over to you, Nick.
Yes. Thank you, Vitaly. And thank you all. I have big shoes to fill. I'll try. I work on material science, on nanoscience, and lately I have been troubled by the fact that in nanometer scale structures, in nanometer scale materials, we use very inaccurate descriptions of their structures. And that's the subject of the talk. It's actually needed in many areas in biomimetic materials when we need to understand the complexity of the structure. And of course, we need to predict it. You will see some examples from all of these technologies, and batteries and drugs are the primary subject of the conversation later. And all of that is connected together by the graph theoretical approach. And graph theory, in my opinion, is something that has been missing from nanometer scale science for a long time. I pressed here and it disappeared. Did I move? So the key points are here on this slide are that the graph theory enables us to understand not just the crystallography, not just the ordered structures, which we deal with very easily and in very conventional manner, but also understand how properties and this order-disorder combination actually work together. They can be used for crystalline structures, for non-crystalline structures, and eventually they are functional. They are not there for no reason, but rather to afford the flexibility and reconfigurability of the structure. Let me give you some examples that we all have. We have enamel, we have bones, nacre, and we have cartilage. Or I hope you do. These are amazing materials. They serve us for many, many years, and we have used them very heavily. Exactly. Coffee and Coke in particular. And yet they work. And the reason is because they are very much a combination of ordered and disordered structures. They self-assemble, and they have the nanometer scale components which can replace the one that have been merged. The similar type of structures can also be obtained or observed in the complex particles that are in biology. They're also self-assembled, also nanometer scale component, also the combination of order and disorder. Very functional. What do we see here? Coronavirus, algae, and pollen particle all have very different scales, but all of them are spiky. And this is a pattern. And I would like to highlight that particular word and that particular property. So it's not an order, it's a pattern. And their functionality is related to the pattern. And their functionality also related to the fact that all of them have lack of order. And let's try to unravel it and how to unravel it. In order to really decipher how it all connected to the properties, we need to have some methodology. And this is the reason why I'm here, to describe that order and disorder. And over quite some time, especially as an onset of COVID, when I actually had some free afternoons to go into the books, I started developing the graph theory of nanometer scale structures. Very simple. So the graphs are important here, and graphs are sets of nodes and edges, as simple as that. They have a lot of tools in order to extract that order and the disorder. And they have a number of parameters to do that, the multipracticality, the connectivity parameters. And the challenge that we will face eventually is how to understand that scalar structure in the context of Cartesian space and in the context of physical space. So let's start very simple. If you have a particle, let's make it a node with the point here that this particle has random shape and say spherical or semi-spherical, or I'm sorry, approximately spherical. We don't know its if it has some aspects. And if the particles are connected, then complex structures will be described by the sequence of edges which indicate these connections, which are normally through organic. Particles, unlike atoms, have geometry. And a lot of particles are rods or ellipses. A lot of particles are nanoplatelets, nanosheets. Some particles are actually chiral. We will have to indicate that geometry, that intrinsic shape of the particles by some graph theoretical representation, and we'll use the representation of pair of the particles for the rods and K3 or a triangle of the particles for the nanosheets, obviously because it's actually find the plane and define that. If we look at the ordered and disordered structures, we can see easily, and we can represent as a graph very standard superstructures from the particles, for instance, chains. And this is the common occurrence in the nanoparticles to form this kind of self-assembled chain-like or one-dimensional crystals, and they can be easily represented in this way. In fact, if we adopt that convention that plates, rods, particles, and maybe even more complex representation, we can describe the entire zoo of nanoparticle assemblies. Really, entire family of all self-assembled structures, which, for example, the maker that we saw before, or some of our rooms here, can be represented by this stack of K3, the triplets of the particles, which are interconnected by the organic lipids. If we look at the pollen and virus and the algae, they can be easily represented by this graph. So the spikes are these rods that we had, and this is the sphere or the loop, which represents the base boundary between the central core and the rest. In this way, we can apply it for any kind of system. And let me give you some examples how it can be used for the development of the drugs. And here is the example of the nanoparticles that form complexes with the proteins. Well, so have you a good introduction to the structure of the proteins? I would like to point out that a lot of proteins form bigger structures. and some of them are in crystallography, and we mine them. And I would like to replace some of the protein structures with the nanoparticles because of these particles can have a number of optical and biological properties that are unavailable for the biological structures. But we need to solve that problem that nanoparticles are rigid objects, or mostly rigid, if you want. And they need to form a complex with intricate structure. Some particles are very sophisticated in shape. They have their organic ligands. They can be chiral. They can be twisted. They can have this variety of shapes which our proteins would need. And the idea of lock and key complexes between the proteins and particles is very realistic, but we don't have tools in order to get to that. And the idea of Emil Fischer is outstanding, but it is a concept. And in practice, it's done only by using small molecules, and the docking area there is actually quite small, and the particles are big. So how do we do it? We have the inorganic particles, and we have the proteins, and the languages there are very different. So the language of the proteins are amino acids. You have a string of bits. We don't have it in nanoparticles. And we have to come up with that the unified language. Let's go and start with the proteins and then extend it to the particles. The typical idea of the protein-protein complex, Emil Fischer, is the distance matrix. When you have a string of amino acids here, a string of amino acids here, and you put in a matrix just physical distance between one alpha carbon and the other alpha carbon. And you have a very fundamental step to finding that language, because if you use geometry, if you use distances, this is the same language for almost everything. And let's go with that, and let's step by step unravel this kind of ideas and see how it works. So we start with the distant matrices, and then we'll look at each amino acid and assign descriptors to that. There are chemical descriptors. There are static charge, hydrophobicity, number of carbon atoms. But what we have done, we introduced two more descriptors. We utilized some of the old descriptors, introduced some of the new ones, and started heavily investigating how the graphs can be used for representing the particle protein complexes. So how that idea that the particle can be represented as a graph. And let's start with the chemical descriptors and try to get rid of them, because the chemical descriptors are the troubles that are very different from particles and the proteins. If you use amino acids, we cannot use the same descriptors for particles. Look at the descriptors. Molecular weight, hydrophobicity, carbon atoms, they all very heavily correlate. Not good. The other point is that amino acids are actually point properties, or in that sense. If we use big complexes, this very sophisticated geometries, it's not enough to know what here is and what here is. We need to understand this as a complex dynamic system. And in order to do that, we need to have bigger measures, not just the point measures. And that's where the geometrical the scriptors come in very nicely. We use the geometries of curvatures and cavities. They were developed by these groups, pocketness, shell accessibility, and inaccessibility radius. As you can see, these are the maps of these parameters on the proteins, and you can see they vary quite a bit. Good. And the scale.
Sorry, it's white low and blue high.
Blue is
It seems to be not the same for all three of them. Other
right.
codes are in excess, but
Yeah,
like it's the other way.
that's right. I actually don't. Yes, you're quite right. We use one for the other and one for the other. But I mean, let me get back to you on that and how to do it. Eventually, it's the contrast that matter basically. And say, I mean, here the pocketness, you can see the pocket here. And it's basically identified that here we can lock the pocket. So if the pocketness fits the accessibility diameter of the particle, they should fit in here. And that's the point. We also used the chirality parameter, which is actually very rarely used in drug discovery. And the reason is, again, because of the point measure. All amino acids that are used in proteins are L, although in bacteria, I mean, some of them can be D, and there are some reasonings that could be used for drug as D. But as we looked at the protein overall, and not just at the point measure, the chirality of the structure can vary quite a bit. And you can see the left and right chirality web on the surface of the protein. And the idea here is that if you have a helix, left helix and right helix, in order for a geometrical object to fit it, they need to match. So left screw has to go into the left thread. Now, we have all these descriptors and we can input them into the matrix. But in addition to that, we need to input also the variability, the reconfigurability of that structure. And with these descriptors that you just seen, we could do. They still remain or the property of the geometry of that rigid combination of atoms. In order to account for that, we started using the graphs. Here, the graphs are more complex than you saw before, but in essence, they are actually very fundamentally identical because they describe the fractality, the connectivity of the particles at the atomic scale. And what is happening here is that we identify the amino acid hydrocarbons, how they connected, and the distances below 7 angstrom, they are connected by the edge. So we translated the language of the graphs to the proteins. The advantages of that now we have a bigger structure which is described as a big structure. And we have now new tools in order to understand how one protein interacts and connects with other protein and look at it in terms of nanoparticles. I'd like to give you some example how the reconfigurability matters here and it can be extracted. There is a parameter called Oliver-Ricci curvature. In traditional graphs in traffic, for instance, or internet connections or likes and dislikes, the social network, it typically describes the essential node, essential network connection through which there is a lot of traffic. Here, if we apply this parameter to the description of the protein graphs or other graphs, it will describe the node which is subject to reconfigurability, which is very easy to change. And this is good because we need to know if we pocket here and there is a reconfigurability node here, this side becomes immediately more likely to form a complex because it enables some freedom.
Before you go on, could you spend a couple more moments telling me what the nodes and the edges are in your protein? You said it went a little quickly, so I didn't quite get it.
Absolutely.
Yeah.
Yeah. So what we have done for the proteins is to put a node for alpha carbon atom and edge if there is another alpha carbon atom at a distance shorter or equal to 7 angstrom.
Okay, and that is that like the pitch of the alpha helix or?
1 angstrom is something. I'm sorry.
Sorry, I was saying what the
Yeah, no, it's not the pitch of alpha helix. It is an accepted interaction distance in the protein community when one amino acid is interacting with another amino acid.
So were you trying to kind of encode some kind of neutral rigidity in the region?
Yes. So if there is a hydrogen bond between the amino acid residue, if they're in proximity and there is some attractive interactions there,
Yeah,
that would be the coding here.
yeah, okay.
Interestingly, that's exactly the same distance that we chose after a lot of testing for our packing density, 7 angstrom.
Yeah.
And then there's a lot of stuff that's not alpha carbons, right? So
Yeah.
are you just for the time being neglecting that or?
For the time being, I'm neglecting those, but I'm very mindful of that.
That's fine,
good
yeah.
stuff.
Yeah,
Yeah. Because we do, if we have all the atoms, it becomes a little bit unruly. Yeah. And now we have a map, for instance, of Ricci curvature on the protein graph, and as you can see, it's actually very variable. So if we want, for instance, the nanoparticles to repeat in that corner or in that pocket, we can fit here quite a lot of particles because that strand can open and close. So this increases the probability for that area or that area to accommodate our kind of liner, our big Titanic that we would like to fit. Speaking of leather, So the correlations here now are much better. So as you can see, I mean, here are this group. I'm really, I mean, you can see that we need to have a lot of repetitions in order to learn. Anyway, so now the correlations are actually not are weak, and this is good because if we have a lot of orthogonality in the parameters, if they describe different properties, different conditions, different aspects of their geometric behavior, this is gives us more features that we can extract the information from, and they are useful, basically. If they are correlated, they're less useful. The other point which I like to make, that if we look specifically at atoms or hydrocarbons, at the interfaces that make the protein-protein complexes, and these areas where lock and key of Emil Fisher actually happens, they are correlated even less. So if we want to establish that surfaces, we get actually more useful information from these parameters than from chemistry parameters. And that's when we started forming these matrices, augment them. These are same distance matrices, but now instead of the two-dimensional matrix, so distance, amino acid distance, we now have multi-dimensional matrices with all these parameters. All the origin curvature, chirality, and pocketness and accessibility. Now,
Can I ask again? Like,
yeah,
Richard curvature, I'm not familiar with.
Mhm.
Is it an attribute of a node or of an edge?
It can be actually both. In our case, it's the attribute of the edge. And now what we want to do is to say, so these are protein bank. We take all the complexes from there, we accumulate it in the machine learning or artificial intelligence. And now we have this big bunch of correlations. Of course, machine learning will be there. And now we want to establish with unknown protein the distances that are based on these geometrical parameters. Maybe some chemistry parameters. It will be the reverse problem. So first we learn, then we have the protein or particle, and we will from this learned correlation, we will establish if it fits here, if it fits here, if it fits there. So this is basically a very, very inefficient method for this the lecture. I'll give you a bunch of numbers and you are lost here, and I'll give you the real punchline. Chemistry doesn't play any role or almost any role in that set of descriptors that were used. So if you look at all in how the accuracy and predictions are for all the protein pairs, if we look at just a combination of geometry and graph theory, and all the descriptors, including chemistry, or some of the combinations with the chemistry, we see the minimum improvement if we add the chemistry to the descriptor parameters, which for every chemist, I am it, is a kind of a heresy. How come amino acids do not care if they're hydrophobic or hydrophilic or positive or negative? The real message here is that chemistry is already embedded in the other parameters. But this,
you lost me also for a second. So what you're putting in as your feature vector is a vector of all of your descriptors. And what's your label? What's the output of the model?
the distances and the predicted distances at the interface. So we have the distance matrix.
Yeah.
There is one protein descriptors, the other protein descriptors, and we are interested at the most likely distances which describe the contact between two chorophylls. Yes, sir.
So, can I, so do you assume there is?
I'll be happy to answer both.
Yeah. So there's enough you're pulling structures from protein database and you're looking at like dimers and trimers and things, right? Is that what you're doing? Like how
Dimers mostly.
Okay,
So protein. One protein.
so you're kind of going through the database, you're finding all the dimers, but they're very generic. The chemistry could be different, the structure's different, right? But you're trying to then see which descriptors predict for the right kind of dimer-dimer contact distances in a sense.
So we're looking at where these dimers are forming the contact.
Right.
Yeah. So this is the output.
Yeah.
We're inputting the matrices which have all the descriptors, all
Right.
and the random forests and others, and XGBoost, they basically crunch it, and establish, so this set of descriptors gives us most likely the high probability of making this contact at this area, and this would be the distances there.
Sorry, I think I've understood what I'm going to answer.
Oh, the same thing.
Well, sort of, I think, yeah, so you don't kind of just take any pair of protein and assume that it's going to interact, you specifically find.
We mind it on the pairs that form complexes.
Okay,
But we can apply it to basically any protein. And we also included the negative pairs as well.
okay. By negative,
I mean, the negative pairs which do not form the complex.
okay.
But we know that they don't make a complex.
And
You need to be balanced there, though.
what does it do when you give it to that don't form a complex? You just say the distances are infinite or?
No. They give that point, the likely contacts, but they're separate points.
Okay.
It's not like the continuous okay. It's
Okay.
more like here, maybe here, maybe here, but this is no continuum in that complex in the lock and key as it should.
Okay.
You know. And we tested it. I'll move a little faster. And we tested it on the proteins that are not a part of the training set, and predictions are actually very good. So the ground truth and the predicted interaction sites match quite well. They match also on a number of different proteins. The real consequence of that we took out all the chemistry descriptors that we can now use on the geometry and graph theory on the particles that are very easily described by this parameter. When we apply this for the carbon sheets, they feed into the meloid fibers, and these structures have been predicted by molecular dynamics. Our predictions fit very well the molecular dynamics with fraction of time. This can be done in 30 minutes. Molecular dynamics has to run in a couple of weeks. We also have done it for a number of shapes of the particles and explained some of the protein absorption specific for the particles. For everybody who likes chirality and the visual idea of testing, we took the carbon nanotubes, which are left and right, and tested the program for a peptide that is expected to form a complex with the carbon nanotube. If you look at the predicted blue sites, they are in mirror image to each other, as they should, because the carbon nanotubes are in mirror image to each other. This is a very clear statement that this approach actually meaningful and working. Where do we go from there? We start applying it to the predictions of interactions of big particles with big proteins, for instance, for coronavirus. And this is the study of the group in Italy and in Spain and Turkey, when they showed that the particles of graphene oxide kill the virus, but it's actually very inefficient, and optimization of the shape of the particle can be given to the form. Now, I'd like to go to the other aspect of that, of the graph theoretical description. And now it will be about composites. You saw the structure of cartilage. Is it messy? Kind of. Does it have order? Actually, it does. And in order to do that, we need to apply that original idea of graph description of the nanostructures. Here, we apply this idea of K2 graphs. These are rods. And the nanofibers are rods. So if we have this rod, this rod, this rod, or fiber, every intersections then become nodes. And after that, we can describe the whole zoo of the solids that are have been used in composites area for a long time, that have these kind of patterns in their structures. Not just the cartilage, it's also the composites from cellulose, foam, graphene, and others. How do we do the graph theoretical description here? Basically now have automatic methodology. We use the computer to analyze these images and to extract that graph. These are the indices that are typical for the graph theory. Some of them are describing short range order, and some of them are describing long range order. Some of them describe singularity points in the structure, which are subject to either reconfigurability, just like ORC, or like order curvature, and some of them are very much related to the transport of phenomena in that system. So, first question first. Can we reproduce the structure of cartilage in something artificial? This is the cartilage. This is aramid nanofibers. These are gold nanowire. We extract the graph theory parameters here, and then plot them on a spider plot. And you can see in the green that gold nanowires form a very different structure than the cartilage. But in the same time, the aramid nanofibers form very similar. All of the parameters here are very close to each other. And from the visual assessment of that, we cannot do it with confidence. We need numbers. And that's why I really like the idea of that if you have a number, H factor or something, but the number gives you the clarity and appreciation of error. Is it close, far away, not? And this is the representation of this is meaningful. This match of cartilage and aramid nanofibers is not just recognized by us in the graph, it's recognized by cells when they are attaching to that composite, and they attach much better to the composite material than to generic plastic. Very quickly, now structure is there. Let's look at the physical properties. So that's a very difficult problem that we face, and now we're just starting to appreciate. So we have the graph, it's scaleless. We can put the nodes and edges, but we need not necessarily the nodes and edges, we need the properties, especially when we deal with the materials for batteries and airplanes. We need to establish how we translate from the network description or the graph theoretical description into something tangible, macroscopic. And here we looked at it at the structures which form by nanoparticles, by the chains of particles. They form these convoluted structures. We extract the graph theoretical descriptions and see that the gel properties, the storage modulus of the gel or stiffness of the gel, if you will, is actually linearly proportional to the nodal connectivity of that gel. Kind of easy, no? So the more connected the structure is, the harder it is to deform. Maybe this is true, but the linearity here is a very important parameter because it gives us the direct connection to the extension of the properties and assignment. This is not true, for instance, for the multifractality that I mentioned. We have the very big jump. It's sigma function almost for the multifractality, and we need to have the continuity here, and we don't have. So one parameter is not the same as the other parameter, although they both describe the connectivity in some way. It's true not only for those particles, but for other particles. These are unpublished data. We just test it again and again. And the average nodal connectivity are very much connected to the stiffness of the gel. These are aramid nanofibers that you just saw. We looked at their parameters, and here not only the average nodal connectivity, but also clustering coefficient is related to the Young's modulus and toughness. So it's not just the soft materials, but also hard materials have the same relationship between these mathematical concepts of connectivity and macroscale physical properties. if you look at toughness or how much energy is spent on the deformation of something and clustering coefficient, connection there becomes very tangible. If we look at clustering coefficient is a triangle. It's basically the three particles, how often these three particles are encountered in the structure. The deformation of a triangle is much harder than the deformation of the line, and therefore the energy expenditures are higher. Batteries are part of it. We need tough materials to include in the batteries, and one of those is that separator that we always neglect. We think about batteries as cathodes, anodes, store charges, but the safety of our cars and computers are actually in that thin plastic membrane. These are nasty things. These are dendrites, which grow from anode through the plastic membrane into the cathode. They create the short circuit, and after that, Tesla has fires, or you have a leak in your laptop. If we zoom in, they're really good-looking structures. I mean, but these are like lifetime fatal. They're good-looking, but they're deadly because this sharp end hears through all the materials, and we need to have strong, stiff, tough material which would be comparable in size to that growth point. And we have it actually. This aramine cartilage-like fibers, they form a layer on the anode of metal, and this is a very thin sheet, and all that can block that this dendrites from forming. Oops. And for your amusement, we can see that we can shoot at the battery as many times as you want. I was at the meeting at Army USA, the generals. And for a good reason, because drones need that kind of battery. And yeah, and if you see the light is still on, so you can shoot, but the battery is still keeping charges. It's not exploding. We integrated in a small company that have drones. Now, the hard part is not on. So this is last couple of slides. So this problem of interconnection between the topological space and Cartesian space need to be dealt further. So it needs to be done for the properties, and the idea, how do we code in not just the connectivity patterns, but also physical properties of each individual fiber? Are they insulators or are they conductors? Are they made from organic materials or inorganic materials? And by the way, how thick are they? All that requires us to look into a variety of connectivity patterns for all these cathodes in the batteries and arrive to a hybrid measure. It's basically just like the matrix for the proteins that you saw before, but in one measure. And one measure matters. So if you have that integrated value that gives you a unified description of connection and physical properties, or the So, or the photometric parameter turns out to have a very direct correlation with the performance of the battery. And we call that parameter, in this case, ohm centrality. So it combines the witness centrality, the thickness of the fibers, and its conductivity in one unit. And this has actually direct translatability. How do we design cathode and materials for the atoms? And this has direct connection to how I think I fit in that discussion. I'll skip this. This is more like microscopy. We need to do it in 3 dimensions, not just in 2 dimensions. And of course, I can skip those because these are folks which cannot be here, but I just a representation of their greatness, and I agree with the point that when students are smarter than you, that gives you like, hey, thank you. I finally see my purpose of life. Thank you so much, and I'm happy to receive questions and comments, and pleasant or unpleasant.
I'll stop the recording. And